The next video in this series will discuss mass spectrometry. It's an analytical technique that measures the mass-to-charge ratio of charged particles. It is used for determining the masses of the particles, for determining the elemental composition of a sample or molecule, and for elucidating the chemical structure of molecules such as peptides and other chemical compounds. Mass spec works by ionizing chemical compounds to generate charged molecules or molecule fragments and measuring their mass-to-charge ratios. The technique has both qualitative and quantitative uses. These include identifying unknown compounds, determining the isotopic composition of elements in a molecule, and determining the structure of a compound by observing its fragmentation. Other uses include quantifying the amount of a compound in a sample or studying the fundamentals of gas phase ion chemistry, the chemistry of ions and neutrals in a vacuum. Mass spec is now in very common use in analytical laboratories that study physical, chemical or biological properties of a great variety of compounds. The mass spectrometer, the instrument used in mass spectrometry, has 4 stages in which it carries out to provide data on the molecule that is passing through it. All this takes place in a vacuum, which prevents the molecule colliding with that of the air. The vaporized sample passes into the ionization chamber. The electrically heated metal coil gives off electrons which are attracted to the electron trap, which is a positively charged plate. Particles in the sample, atoms or molecules, are therefore bombarded with a stream of electrons, and some of the collisions are energetic enough to knock one or more of the electrons out of the sample to make a positive ion. Most of the positive ions formed will carry a charge of +1 because it's much more difficult to remove further electrons from an already positive ion. These positive ions are persuaded out to the rest of the machine by the ion repeller, which is another metal plate carrying a slightly positive charge. The positive ions are repelled away from the very positive ionization chamber and pass through 3 slits, the final one of which is at 0 volts. And the middle slit carries some intermediate voltage. All the ions are accelerated into a finely focused beam. Different ions are deflected by the magnetic field by different amounts. The amount of deflection depends on the mass of the ion and the charge on the ion. These 2 factors are combined into the mass-charge ratio. The mass-charge ratio is given the symbol Mz, or sometimes Me. Only the ion stream you are measuring makes it right through the machine to the ion detector. The other ions collide with the walls where they will pick up electrons and be neutralized. Eventually, they get removed from the mass spectrometer by the vacuum pump. When an ion hits the metal box, its charge is neutralized by an electron jumping from a metal ion. This leaves a space amongst the electrons in the metal, and the electrons in the wire shuffle along to fill it. A flow of electrons in the wire detected is an electric current which can be amplified and recorded. The more ions arriving, the greater the current. The mass spectrometer has uses in many types of industry. It is widely used throughout the pharmaceutical industry for pretty much all stages of drug production. It allows for analysis and the determining of medicinal compound structures. For example, it is used in clinical trials where thousands of drugs are needed to be identified quickly and accurately. It is particularly useful when combined with liquid chromatography. Combined with this technique, it allows for finding out concentrations of drugs in things like plasma, which was previously difficult using just liquid chromatography. Even though it has uses throughout the industry, it is still very limited as to what it can be used for. Mass spectrometers are also widely used in the chemical industry. These include the analysis of gas, as well as for environmental reasons such as monitoring and controlling pollution. There are systems used to analyse volatile organic substances present in things like seawater. For analysing gases, mass spectrometry is most widely used for that of high purity gases, as it provides unparalleled versatility for the detection of contaminants located in pure gas streams. This is particularly useful for the methods listed in the handout. Electron ionization is the oldest and most established of the ionization techniques. Electron ionization is achieved through the interaction of a molecule with an energetic electron beam, which results in the loss of an electron from the molecule and production of a radical cation. Electron ionization is the most appropriate technique for relatively small neutral organic molecules which can easily be promoted to the gas phase without decomposition. Since EI samples are thermally desorbed to the gas phase and subject to a high energy of EI, molecules must be thermally stable. However, a major percentage of the molecules ionized by EI are not completely energetically stable, and a portion of the molecule fragments. However, fragmentation is not necessarily a bad thing, as fragmentation provides structural information as well as a fingerprint means of identification. Chemical ionization, or CI, is a means to ionize compounds in less energetic manner than EI. CI is EI performed in the presence of a large excess of a reagent gas. The excess reagent gas is more likely to interact with the EI electron beam than the molecule. The molecule present in relatively small amounts in a gas plasma, reagent gas, undergo gas phase, acid base, or other types of reactions, proton transfer, Cl- addition, etc. The gas phase chemical reactions result in a removal or donation of a charged species, generally H+, from the reagent gas to the molecule to yield positively or negatively charged ions. The energies of the gas phase acid-base reactions are significantly lower than EI. The lower energy ionization associated with Ci results in a more abundant pseudo-molecular ions, although Ci is capable of generating molecular weight information from labile species. It still requires that the sample be volatile, which could hinder the detection of thermally unstable molecules. Typical reagent gases used in Ci are methane, isobutane and ammonia. Mass spectrometers coupled with GCMS, allows for the online separation of complex mixtures of volatile species, followed immediately by mass selective detection. In addition, GCMS provides a higher degree of specificity than traditional GC detectors and has been extensively utilised in environmental, petroleum, synthetic organic and biological applications. This is a soft ionization technique allowing the analysis of biomolecules, i.e. biopolymers such as DNA, proteins, peptides, sugars, and large organic molecules such as polymers, dendrimers and macromolecules. Desorption is triggered by a UV laser beam. Matrix material heavily absorbs UV laser light, leading to the ablation of an upper layer of matrix material. A hot plume produced by the ablation contains many species of neutral and ionized matrix molecules, protonated and deprotonated matrix molecules, matrix clusters, and nanodroplets. The second step is ionization, more accurately protonation or deprotonation. Protonation, deprotonation of analyte molecules takes place in the hot plume. Some of the ablated species participate in protonation of analyte molecules. The matrix consists of crystallized molecules, of which the three most commonly used are 3,5-dimethoxy-4-hydroxycinnamic acid, or cinnapic acid, alpha-cyano-4-hydroxycinnaminic acid, alpha-cyano-alpha matrix, and 2,5-dihydrobenzoic acid, DHB. A solution of one of these molecules is made, often in a mixture of highly purified water and an organic solvent, normally acetonitrile or ethanol. There are specific qualities to normally look for when deciding on a matrix compound. They have fairly low molecular weight to allow facial vaporization, but they are large enough with a low enough vapor pressure not to evaporate during sample preparation or while standing in the spectrometer. They are often acidic, therefore act as a proton source and encourage ionization of the analyte. Basic matrices have also been reported. There is strong optical absorption in either the UV or IR range, so they are rapidly and efficiently desorb the laser irradiation. This efficiency is commonly associated with chemical structures incorporating several conjugated double bonds as seen in the structure of cinnamic acid. They are functionalized with polar groups, allowing their use as an aqueous solution. They typically contain a chromophore. A mass spectrum will usually be presented on a vertical bar graph, in which each bar represents an ion having a specific mass-to-charge ratio, and the length of the bar indicates the relative abundance of the ion. The most intense ion is assigned an abundance of 100 and is referred to as the base peak. Most of the ions formed in a mass spectrometer have a single charge, so the MZ value is equivalent to the mass itself. Modern mass spectrometers easily distinguish resolve ions differing by only a single atomic mass unit, and thus provide completely accurate values for molecular mass of a compound. The highest mass ion in a spectrum is normally considered to be a molecular ion, however, and lower mass ions are fragments from the molecular ion, and assuming the sample is a single pure compound. Since a mass spectrometer separates and detects ions of slightly different masses, it easily distinguishes different isotopes of a given element. This is most noticeable in compounds containing bromine and chlorine, however there are many other elements with different isotopes. An example of boron is given on the sheet. The relative size of the peaks give you a direct measure of the relative abundance of the isotopes. The tallest peak is often given an arbitrary height of 100. You can find the relative abundance by measuring the lines on the stick diagram. In this case, the two isotopes with the relative abundance are boron 1023 and boron 11/100. These are then used to work out the relative atomic masses of the molecule. Suppose you had 123 typical atoms of boron, 23 of these would be 10 boron and 100 would be 11 boron. The total mass of these will be 23 times 10 plus 100 times 11, which is 1330. The average mass of these 123 atoms will be 10.8. 10.8 is the relative atomic mass of boron. When the vaporized organic sample passes into the ionization chamber of a mass spectrometer, it is bombarded by a stream of electrons. These electrons have a high enough energy to knock off an electron of an organic molecule to form a positive ion. This ion is called a molecular ion. Molecular ions are energetically unstable, and some of them will break up into smaller pieces. The simplest case is that of a molecular ion breaks into two parts, one of which is another positive ion and the other is an uncharged free radical. The uncharged free radical won't produce a line on the mass spectrometer. Only charged particles will be accelerated, deflected and detected by the mass spectrometer. These uncharged particles will simply get lost in the machine. Eventually they get removed by the vacuum pump. The ion, X+, will travel through the mass spectrometer just like any other positive ion and will produce a line on the stick diagram. All sorts of fragmentation of the original molecular ion are possible, and that means you will get a whole host of lines in the mass spectrum. It's important to know that a mass spectrum with an element and each line represents a different isotope of that element. With a compound, each line represents a different fragmented It's important to know that the mass spectrum, with an element, each line represents a different isotope of that element, and with a compound, each line represents a different fragment produced when the molecular ion breaks up. The tallest line in the stick diagram is called the base peak. This is usually given an arbitrary height of 100, and the height of everything else is measured relative to this. It is the tallest peak because it represents the most common fragment ion to be formed. This is either because there are several ways that it could be produced during fragmentation of the parent ion, or because it is a particularly stable ion. Types of fragmentation include collision-induced dissociation, where the molecular ions are usually accelerated by some electrical potential to a high kinetic energy and allowed to collide with neutral molecules, often helium, nitrogen or argon. Electron capture dissociation, ECD, direct introduction of low energy electrons into trapped gas phase ions. Electron transfer dissociation, ETD, induces fragmentation of cations by transferring electrons to them. Negative electron transfer dissociation, NETD, an ion-ion reaction, which an electron from an anionic species is transferred to cationic reagent. Following this transfer event, the electron-deficient anion undergoes internal rearrangement and fragments. Electron-detached dissociation, EDD, negatively charged ions are activated by irradiation with electrons of moderate kinetic energy. The result is the ejection of electrons from the parent ionic molecule, which causes dissociation via recombination. Photodissociation, particularly infrared multiphoton dissociation, IR-MPD, and back-body infrared radiative dissociation, BIRD. It is a chemical reaction in which the chemical compound is broken down by photons. Surface-induced dissociation, SID, used in mass spec to fragment molecular ions in the gas phase by the collision of an ion with a surface under high vacuum. And charge remote fragmentation, a type of covalent bond breaking that occurs in the gas phase ion, which the cleaved bond is not adjacent to the location of the charge.